In this video, we're going to begin our projectile motion subtopic. Basically, projectile motion is just the study of a projectile, and a projectile is basically just an object that has been thrown up into the air and is undergoing a force due to gravity, resulting in a parabolic path or motion. So, all objects that can be thrown or kicked, etc., or launched can be studied using what we're about to look at in projectile motion. But before we delve into projectile motion too deeply, we need to go back over some basics. So at the beginning of every slide, I will have at the beginning of every slide, at the beginning of every video, I'll have the learning intentions from SACE. So this is what they specified I need to teach you. So basically, the first dot point is that uniformly accelerated motion is described in terms of relationships between measurable scalar and vector quantities, which we'll recap, including displacement, speed, velocity, and acceleration. So all really key terminology that you should have learned in stage 1 physics. And if you didn't, we need to go back over them and learn them and understand them. We also need to know that all motion can be described quantitatively using numbers. So these three equations you're going to get very familiar with, and known as the equations of motion. So you don't need to memorize them, but you need to know how to use them all. And you need to be comfortable rearranging them and substituting numbers in and solving problems using these equations of motion. They will be on your formula sheet, so you don't need to memorize them. Now, basically, uniformly accelerated motion is where it's constant acceleration. So for argument's sake, when you throw a ball up into the air, the only acceleration it is undergoing is acceleration due to gravity, which is acting downwards. So it's constant uniform acceleration. And we need to unpack some of this terminology. So, and one more thing. Motion is just basically just any change in position of some object with respect to time. That is motion. Motion is when something is changing position with respect to time. So scalars. Scalars are quantities that only have a magnitude. They have no direction. So something that only has a magnitude. So for argument's sake, distance, which we'll talk about in a minute, is a scalar quantity. It only has a size or a number. No direction. Things like amounts of energy, so kilojoules or calories, they don't have a direction. Temperature doesn't have a direction, it's just a number. Whereas vector quantities have a number or a magnitude, but they also have a direction, and the direction is important. Most things in physics are vector quantities, okay? They have a magnitude and a direction. So for argument's sake, a force, it might be a 10 Newton force, but it might be applied downwards or to the right, etc. Forces always have a magnitude and a direction. Quantities that you would have looked at last year include velocity, acceleration, momentum. They're all vector quantities. They will have magnitudes and directions. Now, we're going to fill out this table. So the symbol for distance, in case you don't remember, is S. The reason being is S is basically for space. Now, it is only a scalar quantity because it doesn't have a direction. And the definition of distance could be something as simple as how far an object has travelled. Apologise for my penmanship. How far an object has travelled in total. So it's the total distance an object has travelled. Whereas a displacement, if you can't remember displacement, that's fine. But displacement has a different meaning completely. Now, a displacement has a symbol S with a little arrow above it to signify it's a vector, so that's displacement. And it is a vector quantity. So displacement has a size or magnitude, but also has a direction. So for me, displacement, to define it, I would say the change, the change in position of an object. I do not have enough room. So the change in position of an object from its initial point, from its initial starting point to its final position, including a direction of travel. I did not have enough room, I apologize. Including a direction of travel. So, if you need me to explain this in more detail, so say an object starts here and it finishes here, but the path it took was this. So this here would be its distance. Its distance traveled would be its total distance traveled. However, its displacement is just the change in position of an object from its initial starting point to its final position. So this here is the displacement, and it includes the direction of travel. So it might be this, if it was a compass here, that might be south east. So it might be 10 meters southeast. So displacement has a direction. Now speed, the symbol for speed is v, and it is only a scalar quantity. Now the definition I'm not going to write there, I might just write it up here. Now, the definition for speed, well, if you think about speed, you think about how fast an object is traveling, but a physics definition for speed would be something like the distance traveled, so the distance traveled of an object over a given amount of time. This pen is being a pain. I apologize. I'm not going to restart it, but this pen is being a pain. So distance traveled an object over a given amount of time. So speed, remember, is just distance over time. And we have units of meters per second or kilometers per hour. Now velocity, similar, but velocity, the symbol for velocity is v with a little arrow above it. And it is a vector quantity because velocity has a direction. So the only difference is, well, speed was distance over time, well, velocity is displacement over time. So basically velocity is, well, I would say that's the rate of change of displacement. The rate of change in displacement, if I was defining it. Or you could say that it's basically the displacement of an object over a given amount of time. Velocity is displacement over time. So, just to recap displacement, if a athlete travels 400 meters around a track, so you have a 400 meter athletics track, and an athlete starts at the starting line and finishes back in the same position. His displacement is zero because displacement is a change in position of an object from the starting point to the finishing point. So the displacement is zero. Now, velocity is displacement over time. So if an athlete has traveled around the track and starts and finishes in the same spot, his displacement is zero, therefore his velocity is zero, because velocity is displacement over time. The last thing we're going to look at is acceleration. Now, the symbol for acceleration is A. Technically, it's got a little arrow above it, but we usually leave that off. It's also a vector quantity. So, acceleration can be defined as the change in velocity over a change in time, or the rate of change in velocity. So, the change in velocity, I'll say the change in velocity over time. Over a given amount of time. I should just type these definitions out. Hopefully you had more room than I did, and a bit more successful than my pen. I need to get used to writing with this. Okay, so acceleration is the change in change in velocity. So delta V is change in velocity over change in time. Hopefully those definitions are recap. If you completely forgotten them, that's fine. But we'll go back over them. Displacement, velocity, acceleration are the key ones. Now, these equations of motion. I'm not going to prove these equations of motion to you, but I can prove them to you. They all work. This first one, for example, if we were to rearrange it, it's that acceleration is final velocity, take initial velocity, so it's the change in velocity over the change in time. And if we rearrange that times both sides by t, we'll get at, and then add v0, so we'll get final velocity is v0 plus at. That's how we get that first one, and I could prove the rest of them to you. I'm not going to waste time on that. You don't need to memorize them, they'll be on your formula sheet. So S with a little arrow above it is displacement. The standard international unit, SI unit, is in meters. So we always need to convert it into meters. So if it's given in kilometers or centimeters, for these equations to work, it needs to be in meters. Final velocity is meters per second. So remember, we generally don't write m over s. Sometimes we do. Actually, it doesn't really matter if you write m over s. That's fine. But usually we write ms to the minus 1. So the v by itself is final velocity. Some people like to do the little f. I don't mind, final velocity. But this is how it's given on your formula sheet. Now v0 is initial velocity, 0 for time of 0. That's also in meters per second. So you need to convert it into meters per second. Acceleration is in meters per second squared, because remember, acceleration is a change in speed or change in velocity, so that's measured in meters per second, over a time which is in seconds. So it's meters per second, which using index notation we write as meters per second squared. And the last variable is time, and time needs to be converted to seconds. So if it's in minutes or hours, etc., we need to convert it into seconds at all times. So these are our 3 equations of motion. I'll give you a hard copy formula sheet, and I'll also attach one to DayMap. So we're going to do a few problems just to get us back into the swing of using the equations of motion, which you should have had some practice in at stage 1, year 11 level. So those are our equations of motion. So I'm only going to do, I think, 2 equations and then a little bit of rearranging equations. I'm going to get you to do some practice problems. So what I want you guys to do as you're doing practice problems is just read carefully. If it was a test or exam, you can underline keywords. So an airplane needs to make an emergency landing on a runway that is 800 meters long. The airplane touches down on the runway with a velocity of 85 meters per second and decelerates at a constant rate of 5 meters per second squared. So that's its deceleration or its acceleration. It takes 17 seconds for the aeroplane to come to a complete stop. 17 seconds, so we have a time. Will the aeroplane stop before it reaches the end of the runway? So I'm not going to draw the diagram, but we have a plane. We need to see how far it will be displaced. It has a runway of 800 meters, but we need to find out whether it's going to stop in time. So what key information do we have? Well, we have the length of the runway, but we don't have how far the thing has traveled. We actually want to find, that's what we need to find. Displacement is what we are looking for. Usually we can be lazy and we don't have to write the arrows. It's fine just to write S for displacement. I know it's distance, but it's a bit annoying drawing the arrows all the time, so you can get away with it. Now, what do we know? The airplane touches down on the runway with a velocity of, so that's its sort of initial velocity. That's what it's starting off at. So its initial velocity is 85 meters per second. Pretty quick. And decelerates at a constant rate of 5 meters per second squared. So as soon as you see per second squared, that's your acceleration. And it's decelerating. So because it's opposing the motion of the plane's going in this direction, the acceleration is opposite, decelerating it. So when we're looking in one dimension, backwards and forwards, we use negative signs to signify direction. So if our velocity is positive 85 to begin with, moving to the right, well then our acceleration needs to be opposing that, opposite, so it's going to be negative 5 meters per second squared. Whoops, different notation, doesn't matter. And the last thing was that we were given the time. So the time is 17 seconds to come to a complete stop. So we have the initial velocity, we have acceleration and time, and we want to find displacement. So when using these equations of motion, you need to work out which one we can use to find displacement. This first equation has no displacement in it, okay? This one does have displacement, and this one has displacement. So what you need to then do is think about, well, what information do I have? Can I use this one? I've got the initial speed, yes. I've got the time of the motion, yes. I've got half. I've got the acceleration, time. So this one is good. I've got all the information. I don't have to rearrange it or anything. So I have the displacement. I mean, I can use this formula. This one here, well, I don't actually have all these things. I don't have... Actually, I do have its final speed. Its final speed would be 0, but we would have to rearrange this one. So much easier to use this one. So we can work out the displacement of the plane. So the displacement is, write out your equation. I want you to get used to writing out the equation first. And then substitute in. So first, this is the steps you need to take. This, you're not going to get marked down if you don't write this down. This helps you sort out the problem. The stuff on the left helps you sort out the problem. But you do need to write down the formula, and then you need to substitute in. So V naught T. So V naught is 85 times by the time, 17 seconds, plus a half, which is 0.5, times the acceleration, so it's -5. So that's so vital that it was -5. Completely changes your answer. Times by the speed, the time squared. If you type this into your calculator, practice. It's actually really easy to do this on a graphics calculator. So I would recommend learning how to use your graphics calculator. So it's 85 times 17 plus a half times by -5 times by 17 squared, and do it all in one big line. And I got, when I typed it into my calculator, I got 722.5 meters. Now, in general, and I'll make this more clear later, based on how many significant figures you get in the question, that's how many you do your answer to. So we got given numbers to 2 significant figures. 85 is 2 significant figures. 17 is 2 significant figures. 5.0 is 2 significant figures. So everything is 2 significant figures. So I won't go into too much detail now, but 7 then the 2 is significant. So to 2 significant figures, this answer is actually 720 meters. I know you're losing some accuracy, but in the test and exam, you actually need to write answers to the correct amount of significant figures. So, will the airplane stop before it reaches the end of the runway? Yes. The plane will be fine. Fine, as 720 meters is less than the 800 meter runway. Next question, example. So, a ball, and the ones that I'm giving you are actually going to be mostly vertical motion problems. So a ball is thrown vertically upwards with a velocity of 4.5 meters per second. How long does it take the ball to reach its max height? So basically we want to find it at its max height. So if you throw a ball up into the air, it reaches its max height, what's the ball going to be doing at the top of its flight? It's going to be stationary for a split second. So its final velocity is going to be 0 meters per second. Its initial velocity is the 4.5 meters per second. We don't have much information. We want to find how long does it take. So time is what we're looking for. We've got the final velocity, we've got the initial velocity. I've only got 2 bits of information. You always need 3 bits of information to find a fourth. Now, what we do know is that we know that at Earth's surface, the acceleration due to gravity is constant. It's always 9.8 meters per second. That's a 9.8 meters per second squared. This is on your formula sheet as well, the acceleration due to gravity, but it's always acting down. So if our initial speed is 4.5 positive going up, well then our acceleration needs to be negative because it's acting downwards. So we've got final velocity, we've got initial velocity, acceleration, and time. So we need to look across at our equations, and we need to see which ones involve time. Well, the last one doesn't have time in it, so that's useless. And then this one and this one have time in it. This one has displacement. We don't have displacement, so we can't use that one. So look at this one. Do we have the final velocity? Yes, because it's stationary at the top of its path. We've got the initial velocity, 4.5 meters per second, acceleration due to gravity, and we can rearrange this equation to find time. Now, I'll do some rearranging, I'll help you with some rearranging, but you need to first write out the original equation. Now, in physics, I don't actually like to show a lot of working when I'm rearranging equations. If you need to, that's fine. And I was going to do a little bit of rearranging equations on this page. But if what I'm saying now isn't making sense, I'll help you with this more individually. So we want to get time. Time's what we want to solve for. So we need to rearrange this equation. First, we want to get rid of the V0. So the rules of rearranging equations is, well, this is positive V0, and we want to get rid of it onto the other side. So we need to do the opposite process. This is plus V0. So we're going to take V0 from both sides. Okay? I'm not going to do all the working, but we're going to get V take V0. And then it will cancel out from this side, and we'll get V take V0 equals AT. We then need to get T by itself, so this is really A multiplied by T. So the opposite of multiplying by A is dividing by A. Oh, I might as well show you. And then they'll cancel out, and we'll be left with, T equals, the A's cancel out, T is equal to V take V0 over A. Now, if you struggle with rearranging equations, you need to learn and practice, because it is the crux of problem solving in physics. And now that we've rearranged the equation, now we can substitute in our known values. So the final speed of the ball was 0 meters per second. The initial speed of, or the initial velocity of the ball was 4.5 meters per second. And then the acceleration due to gravity was negative 9.8. And when you type this into your calculator, it's a minus divided by a minus, which will give you a positive time. So if you'd stuffed up the acceleration, it just would have given you a negative time value, and then you would have realized, oh, I needed to make acceleration due to gravity negative. So it's negative 4.5 divided by negative 9.8, and that gives me 0.459. But if we look up, how many significant figures do we have in the question? We only have 2, so this 0 is not significant. So we can write this as, I'm not going to do scientific notation now, we'll just write this as 0.46 seconds. Now, I'll do a little bit of rearranging equations here. So this first one, V equals V0 plus AT. So we just rearranged that. If you look at this top equation, we rearranged it for T. So T, first we had to get rid of the V0, so we took V0 from both sides, and we got V take V0, and then we divided through by the A. So once you get the hang of rearranging equations, you're not going to write out the steps. You literally will look at it and be like, well, it's going to be V take V0, and then all that's left will be the A, and I'll divide through by the A. So the time will be V take V0 over A. Again, if we wanted to solve for V0 and get V0 by itself, well, we need to get rid of the plus AT, so we need to take AT from both sides. So V0 will be the final velocity take AT. And the last thing you could be required is you could rearrange this for A. So if we want to get A by itself, first we'll take away the V0, so it'll be V take V0. But then this time, to get A by itself, we're going to divide through by the T. And that's actually our definition of acceleration. Acceleration is a change in velocity over time. So that's rearranging those equations. They're all pretty much similar, or they're not all similar, they're all different. This one's a bit more complicated. And this middle one, usually V0, when we have to rearrange this one, usually V0 is 0. So often we're left with something that looks like this to rearrange. And often this one requires us to rearrange for T. So to rearrange for T, I might do this one in steps. So we want to get T by itself. It's T squared at the moment, and there's a bit going on. So usually what I like to do is, to get rid of a half, you might say, well, a times a half. To get rid of a half, you divide by a half. But another way of getting rid of a half is timesing both sides of the equation by 2, because half times 2 will just be 1. So timesing both sides of the equation by 2, you get 2s. So you get 2s equals at squared. And you want to get t by itself, so you divide by a. So it'll be 2s divided by a equals t squared. And then finally, you want to get t by itself, and the opposite of squaring something is square rooting something. So t is equal to the square root of 2s over a. You'll get to a stage where you look at this equation and you'll be like, alright, we want to get t by itself, get rid of the half times s by 2, so it'll be 2s, divide 3 by the a, 2s over a, and then square root it. So you literally will look at this and you'll be doing that in your head. You also obviously need to be able to arrange this for a as well, the acceleration. But generally in physics, you're given the acceleration, so it's not, which is the acceleration due to gravity, so you're not often actually having to rearrange it for a. This equation here, again, similar. I'll just do a couple things. So if you want to use this equation, it's final velocity squared. So to get your final answer, even v, it's going to be the square root of v0 squared plus 2as. So the square root of all of that added together. V0 squared, so V0, first you would have to take 2s, so to get V0 you have to do V squared take 2as, and then you would need to square root it, and so on and so forth. I could do the same. We could solve for, I won't do it for a, I'll solve for s though. So if you needed to use this equation to rearrange to solve for s, you want to get s by itself, so you do the opposite. So you want to get rid of this, so you're going to take v0 squared from both sides. So it'll be v squared take v0 squared, and then you're going to be left with 2as on this side. And if you want to get s by itself, you're going to have to get rid of everything else. So this is 2a times s, so we're going to have to divide both sides by 2a. And we'll be left with s equals v squared take v0 squared divided by 2a to find the displacement of an object. So, if you need help rearranging equations, I'm here to support you, but what I want you guys to have a crack at now is there will be a handout on daymap, and you'll be practicing just 1D motion, so motion just going up and down. Okay, just remember that we're always going to have the acceleration due to gravity as negative 9.8 meters per second squared. And when you're throwing balls into the air, when it's at the top of its flight, its velocity, its final velocity is 0. Or if you're dropping an object, you're dropping a ball downwards, its initial velocity is going to be 0. But have a go at the questions. The answers are there, but not the working. But yeah, let me know if you have any issues. Thank you.